Hi, my name is Brian Berzin, and I'm co-founder and CEO of Thea Energy. Thea Energy is a fusion technology company building an economical and scalable system architecture utilizing arrays of mass manufacturable magnets and dynamic software controls. Our flavor of fusion technology is called the stellarator, and we've reinvented it to leverage these programmable magnet arrays. The result is a more practical form of commercial fusion energy that can be deployed at scale. Thea Energy as a company is about 3 years old. We spun the company out of the legendary Princeton Plasma Physics Laboratory, where the stellarator was actually first invented, and I'll get more into that shortly. Today we're about 70 employees, as you can see in the labs behind me, where we manufacture, design, test these magnets all in-house and build them to fusion relevant scale. The stellarator is a form of magnetic confinement fusion energy. The stellarator and the tokamak are probably two of the most studied forms of magnetic confinement fusion energy, where we utilize large electromagnets, in our case superconducting magnets, to confine a plasma in a very specific configuration. A plasma is a fusion fuel. So within these toroidally shaped devices, where the plasma is kind of connected in a toroidal configuration, these electromagnets confine it in a very specific configuration. The difference between the tokamak and the stellarator is really this twist in the magnetic field. Where a tokamak, every slice is symmetrical, and therefore it's a lot easier to build. The stellarator looks like this French crawler. And by putting that twist into the system into the plasma, you actually are creating a magnetostatic, a steady state configuration. And that, and this is prior to even Thea Energy being founded, that's always been a real advantage, and one of the reasons why the stellarator has always been seen as a leading approach to a power plant architecture. Because in a power plant, the goal is to create energy continuously, not just for a fraction of a second. You want to put energy on the grid to utilize 24/7. So that steady state nature of the stellarator and its high efficiency are some of the reasons why it's become one of the main focuses of fusion research across the world. Unfortunately, building a device that looks like that specific twisted configuration is very difficult. And over the past couple of decades, there have been multiple large-scale integrated stellarators, and the usual result of the system complexity and precision are cost overruns and schedule overruns. And this is a pretty universal rule here, that complexity and precision in hardware is just very expensive and very time consuming. And for reference, this is a picture of W7X during its construction. You can see a couple of people in the background that are working on the device. That really puts into perspective the scale of these superconducting magnets in the middle. So for fusion devices, for Thea and other stellarator approaches, these are multiple meters tall superconducting magnets. And if they're 3D, if they're that twisty shape, even though they're 2 meters tall, they have to be within millimeters of precision. That's just very expensive and very time consuming. And so a number of these devices that were built went 10 years behind schedule, billions of dollars over budget. And while that's allowed for a first-of-a-kind scientific research project, if you're building a power plant based on these technologies and the result is billions of dollars of cost overrun in a decade of schedule overrun, that's not a very good product. So the foundational concept behind Thea Energy is, how can we eliminate from hardware precision and complexity? And to be clear, we're not proposing any magic bullet here. We are not eliminating precision and complexity outright, but what we are doing is we're transferring it from hardware to software. So within our architecture, we utilize an array of about 400 planar superconducting magnets. These magnets, and this is a 3D printed plastic version of one from our first generation. These are smaller, wound in tension around a bobbin. These are one of the more simpler forms of electromagnets out there. And within the array of about 400 magnets, every single magnet is actually identical. They're all the same. So they can all be mass produced via simple means. And then the special part is the software control stack. This is no different than how radar systems work or cell phone towers. It's called a phased array. So we, within our software stack, are able to control every single magnet independently, just like the pixels in your computer screen right now. So every pixel is the same, but they're dynamically tuned so that you can see really complex, really high resolution images, even though the hardware is all the same. So within our array of about 400 magnets, we utilize a very complicated software stack to individually control every single magnet to make the very complicated, very precise magnetic fields required for this stellarator system architecture. And over the past year and a half within our walls at Thea Energy, we have actually built and operated what is now the world's first array of superconducting, high temperature superconducting magnets. And so this array, dubbed Canis, operating in a room behind me right now, was instrumental to us to verify the performance and show that we can create these very complicated magnetic fields, but with simple hardware. So we did that earlier this year in 2025. And from there, we actually continued the testing and operation of this device to show the practicality of this simple hardware, complicated software that's dynamic. And you can probably see it from this image on the left-hand side of the screen. Every single magnet has dozens of sensors within it. So we can tell voltage, current, magnetic field, temperature, across many points within the array. And from that, we've trained what I'll refer to as a closed loop control system. And actually earlier this year, we published the results of this as well. And that has now actually been peer-reviewed and released just over the past couple of weeks. So we're excited to talk about this, not just in a press release format, but to actually provide our peers with the data, with the support to show why this is such a big deal. Following that, over the recent few months, we have been purposefully throwing curveballs at this array because we are really only now starting to understand the capabilities of a dynamic software stack. And so within the array, you can see a picture on the left-hand side of the screen, we have actually mismounted a magnet by over a centimeter. So that's about an order of magnitude more hardware defect than a modular coil stellarator can tolerate. And within the array, we mismounted the magnet, we mismanufactured it, we put it back in. We didn't actually tell the control systems what we did. But because there are so many data sensors and instrumentation in there, that the software stack knows exactly what's happening. So in the array and the software, that magnet gets slightly turned down and the magnets around it are turned up slightly. And when we verify the magnetic field via some very specific Hall probes, they're virtually indistinguishable, even though there's a massive hardware defect. That is a practicality that I think is really important and new to the stellarator that is now enabled by this architecture. Over the past couple of decades, I think the world and the research programs from which we spun out were very much focused on proving out the science to show that fusion is possible via these architectures. Where I think we are transitioning to now and where the industry needs to focus on next is how you commercialize that in a practical format. So when you build a power plant, I think it's a safe bet to believe that on occasion things are going to be slightly mismanufactured or mismounted. That's just the reality of the world. If you don't have to manufacture every single piece of hardware to 0.001 millimeter precision, you can use more standard manufacturing processes. You'll have more efficient processes as well and more economical. So that's only one part, the construction and manufacture of a power plant system. What happens then over a period of a few decades is that systems will have wear and tear. This is no different from any other type of thermal power plant out there, to the cars we drive, to the aircraft that we fly in. Over operating lifetimes, you have parts wear out. You have things that need replacement. Most of fusion right now is focused on perfect lab environment conditions to make fusion happen for a fraction of a second. We at Thea are really trying to focus on what happens when magnets or other system structures wear over time. And that's something that allows us to have a system architecture that can self-tune, that can dynamically change parameters as this happens over the course of days to months to years. And therefore, you'll have a device that continues to run at a higher capacity factor with a lower O&M maintenance cost. That is the practicality that we're really, really focused on. Another major advantage that we've really just started to uncover here is by having a software layer that touches all parts of the system and can tune things. We now have an architecture that over time we can actually provide the system with updates. So there are parts of this world, especially for fusion research and plasma physics, that we're continually advancing and we're continually getting better at it. Turbulence modeling and suppression is one of those areas. So we, over the next 5 and even 10 years and beyond, we will continue to have better models and simulation tools for understanding turbulence and ultimately to making lower turbulence in your device. And for most other fusion architectures, this is something that if you learn something new, you redesign the system and the next one is better. But this one is kind of stuck where it is forever. With this architecture, with this phased array approach to the stellarator, we have an advantage to provide the system with a software update, a control system update, and therefore actually have higher performance even though the fixed hardware is the same. So this is something that enables continual improvement of a fixed asset rather than just, oh, we can learn and do better for the next machine. So I've spent a couple of minutes here talking about the advancements and the results to date with our hardware. I want to talk a little bit about where we're going and the path to actually commercialize this technology. So we're getting really good at manufacturing these superconducting magnets. We're scaling up production. We've built the control systems that we need. The next step for us is to build an integrated system based on our technology. This device, which we call EOS, will use our planar coil system architecture to create a decent high triple product and also do so in steady state, as pretty uniquely only the stellarator can do. So this device is our proof of concept that not only shows an integrated system fusion performance, but just as importantly is a 70% linear scale of a power plant, so a large scale system that allows us to do all this systems integration, procurement, and engineering of a power plant scale device. So science, really important to fusion. Technology and engineering, really important to fusion. A lot of the practicality of operating utility scale power plants comes with the execution and buy down of programmatic risk of actually constructing the device and the facility. So this upcoming project, which we plan to have operational around the end of the decade, allows us to go one step further than just system technology development and scientific verification. It allows us to buy down the programmatic and execution-based risks of a power plant scale asset. So this device for us, we're going to be nearing about the 10% design completion later this year, at which point in 2026, next year, we will actually choose a site as to where to build this. So some really exciting stuff coming up for Thea Energy. And by designing, constructing, and operating that device, we have a really clear path to how we commercialize the technology and its final architecture, a power plant. So this device will be a scale-up of EOS. It will also change the fuel mixture. EOS will be a DD fusion device. It will be a subscale. We are going to be working towards a DT fusion power plant. And by changing the fuel mixture to DT, scaling up, we will have a very efficient system in terms of its ability to create on-the-grid electricity. And so double clicking in on that one for a second, within the various fusion architectures being proposed now, a lot of people are thinking about Q greater than 1 on a scientific basis. The stellarator, the advantage of the stellarator that we're really focused on commercializing is back to the beginning of this conversation relating to the steady state nature of that plasma. And this, what is on the screen now, this was actually a study done in about 2012 that looked at a number of power plant architectures for fusion. And it sized them based on a very similar magnetic field at the coil. And one thing that was apparent via this peer-reviewed study was that even if you make a tremendous amount of fusion energy, there's always an amount of it that has to be recirculated into the device. And so the stellarator shines because in a stellarator you can reach this point of ignition. Ignition is a self-heating plasma where you get to turn off a lot of the energy recirculation. And that allows you to have an architecture that creates a lot of energy, and then you can put that energy on the grid rather than having to pump it back into the device to restart a reaction, to squish a plasma. There are a number of different ways of how you would potentially want to recirculate energy and inertial confinement and other forms of magnetic confinement. But for the stellarator, it's a complicated system with that very specific French crawler shape. But if you can make that device, you can create a highly efficient power plant architecture where most of the energy created then can be utilized for the real goal to create electricity to put energy onto the grid. So we're really excited that the path to commercialize the stellarator from building an integrated system, because it is steady state, scales from an economics perspective very nicely to a power plant. So I hope you learned a little bit more about what we're working on at Thea Energy and why we're really excited to commercialize our planar coil stellarator technology. Looking forward to continuing the discussion here later today as part of the Q&A. Thanks again. Bye now.